Open Research Seminar. This is, we proceed with a series of open research seminars dedicated to the annual research conference, which will be held later this week in Krakow, together with National Bank of Poland. And today we have our colleague Mihnea Constantinescu, who will talk about the paper, or about the project that was actually very useful for us, for the National Bank of Ukraine during nowcasting processes at the National Bank of Ukraine. So Mihnea will talk how to evaluate the current economic stance using alternative data. So Mihnea, please, the floor is yours.
Great, many thanks. Can you hear me? All good.
Yes, we do. We can see your slides.
Very good. All right, so доброго дня, everyone. As Sasha mentioned, this is a project that was started in March, April, and it was a mix of finding proper data and proper models to nowcast GDP. So within the literature on nowcasting, in a sense, there are some established methodologies, such as the one by Giannone, the one by Dotz et al., which make use of a lot of time series. So you have maybe up to 100 different variables tracking various aspects of your economy, consumption, investment, firm behavior, and so on and so forth, which can be used to guess, in a sense, what the current GDP is at the end of the quarter during the quarter. So the exercise starts usually in January, and it's more of a forecasting of what GDP will be in March. As you go to February, there's new data coming in, you update your March value, and then as you get into March, you then have some form of preliminary estimate of GDP. Why this happens like this is because statistics generally takes anywhere between 2 to 4 months, maybe some even more, to actually come out with a final GDP number. So we will know for sure what happens in March only in June, July. And that was exactly what we were facing during COVID, and this is exactly what we were facing during the Russian invasion. So the COVID experience, it's actually quite useful because a lot of novelty in terms of both data and methodology was introduced. So there are a bunch of papers that are included here, but they're not the only ones. So this is just a small highlight. In February, every data gathering process of both state statistics and private companies was frozen. So we didn't have hard or soft variables. We did not have statistical data. We did not have surveys of companies in the traditional way. And it was not clear for how long this would go. So we needed to cook up, in a sense, a different way to understand this exercise. And this is how this project was born, out of the need to both gather additional data, alternative data, and to test how this data might be useful to nowcast GDP. So in a sense, we are not starting from scratch, because nowcasting or estimating GDP without any official statistics has a tradition in the literature. In the development economics literature, there are papers that look, for example, at what is the stage of income or economic development of countries that don't actually have official statistics, Central Africa, and so on and so forth, using nightlights. As soon as the internet came in, this represented an alternative, very useful possibility to gather data, usage of mobile phones as well. The main challenge with this is that the literature and the models themselves were developed and tested using peacetime data. And during a war, you can expect that many things change with respect to the parameters that you normally estimate during peacetime. So both nightlights and Twitter can possibly flip signs during the course of an invasion, leading so to inconsistent parameters. So for us, this is quite simple to understand. If you look at the cross-section of Ukrainian regions or cities, you will see that the regions and cities that have the highest GDP also have the highest luminosity. So Kyiv has the highest luminosity, both in terms of light per square meters, as well as total intensity. Less developed economies or regions have then less light. Same story with Twitter. The literature here identifies Twitter activity with pictures as being a proxy for income. How does this change during a war? Well, with lights, we had light masking introduced, I think, in April, where the officials asked people to cover their windows in order not to give any sort of sense guidance to potential attacks. So public lighting was also turned off, and so on and so forth. Nevertheless, there was electricity, and people continued to work or consume, not to the same degree as before, but it was not completely interrupted. Twitter before the war was pictures about your new car or your holiday abroad or whatnot. So the more you had social media activity with a picture, the higher was the income of the region on average, and we observe exactly the same behavior and the same relationship across Ukrainian regions and cities. But obviously, as soon as the war starts, Twitter becomes an information tool, and pictures are very much about destruction, are very much about completely different things. So before the war, we would estimate a positive correlation between these, and that positive correlation would actually tell us that the more a region is suffering from destruction, the higher would be the GDP. So completely counterintuitive result. On top of this, Twitter data can now only be accessed for a fee. So before, until about mid last year, this data would be available for researchers for free. Now you have to pay for it, which makes it less attractive. The night lights data can be obtained from NASA. You can get these pictures of entire regions, and you can create your own index according to your own needs. The third category of data are Google Trends. They're not entirely immune to many of the things that I've talked about before, but they seem to be more robust in this respect. And this is also what has been used mainly in the literature in nowcasting. So if we look at this, there's already a split in the literature, if you wish. Development economics works quite a lot with social media activity, Twitter, Facebook, where data is available, and nightlights. If we talk about macro literature on nowcasting, it works more with Google Trends. The overlap is not, the overlap between these two exists, so you can have models that use more or less 2 out of these data sources, but this is generally the way you find papers. So this means, I'll talk exactly in a moment why this is the case. This means that we need to understand how this data actually can be distilled and used in a nowcasting model. So we might need to look at different factor model specifications or different types of estimation. The other thing that was also very interesting, at least for us, is that during this first period, we had very asymmetric effects of war. So there is the siege on Kyiv in March, April. As soon as this goes away, we see actually a rebound in activity in Kyiv. Because of internally displaced people, we have regions in the west and southwest that actually observe higher economic activity than there normally was the case. And this is because many internally displaced were looking for a place, maybe to stay, maybe to go further away, but this put pressure on rents, for example, and led to more consumption. Structurally, as the government steps in to help companies relocate, we now also see that firms establish their bases again in the west and southwest. This means that there might be scope for a regional factor model, because war affects regions quite differently, and we can get the expected negative impact in those regions close to the front, but we might actually get positive impact on regions far from the front. And when we interpret national statistics, we have to be aware of these things because, in a way, if the weights of the regions are more or less similar, and so on, and the sizes are similar, we might actually end up with no change, even though structurally there's a lot of change in our economy. This is the research context. Within this broader research context, you can also find papers that work with payments data, which are very interesting. So there's Galbraith and Kach, 2018. There's Chapman and Desai. I think they even have an update to this paper, so it should be 2022. In April, when we started this, we did not actually have updated cash data, so we didn't really know if this were viable, but they became very useful afterwards. So time series on cash usage are very well correlated with regional economic activity. My colleagues, including Sasha here and Andrei, were working with electricity, we're working with mobility data from Google and Apple, but many of these are then interrupted for security reasons. Access to them is no longer granted during the first stages of the invasion. So, we start off from a potentially very large list of alternative indicators, but then depending on our application, we start understanding that some of them might actually not be useful, some that are useful are not available, and we're pretty much left with a small selection of things we can use. The main issue from the perspective of the existing models, so Giannone and Dodds that I was mentioning before, is many of these variables, whether it is night lights, whether it is Google Trends, whether it is social media, may have little or no connection to the assumed latent factors driving GDP. And this is why, at the end of the day, we probably need, and analysis will show that to be the case, we probably need a different factor model and we need a different estimation strategy. Remember that nowcasting models use up to, let's say, 100 time series of variables that we know are economically relevant, such as what firms invest in, what consumers choose, and so on and so forth. So these are directly connected to GDP. Many of the variables that we will be looking at are not necessarily directly connected, and we don't have a theory that says this particular search online is good to estimate GDP. And this seems like a little trivial point, but you will see when we talk about using the methods, this is not the case, because the Giannone model and the Dodds model using these variables do not produce the same outcome as the updated algorithm. What data do we end up having? We have quarterly GDP in the aggregates up to Q4 2021, and we have regional Ukrainian GDP data up to 2020. There's no 2021 in March, April, May when we were doing this exercise. As well as we have Google Trends, both aggregated for Ukraine as well as regional values. Very quickly, for those who haven't seen this data or haven't worked with this data, Google Trends data are time series that you can download for free from Google, and they represent search volumes, and they're built as indices that capture volumes of keywords associated to a particular category or topic. So, for example, you have here a category related to car. I made this example for car, but it could be anything else. It could be washing machine, which we actually use. It could be a particular brand like BMW, which actually ends up being a topic, and so on and so forth. Categories are consumption, labor, transportation, investment, education, inflation, economy, default, legal services, and so on and so forth. What these are relative indices. That means they do not give us an exact number telling us so many people are looking for this particular topic. They are relative to the search that is the most popular in a particular area in a particular period. So if, for example, as it happened in 2022, we have in February, let's say war is the most important search. This gets a number of 100, and all the search volumes of the other topics are related to this. Okay, so then, something that's going to be just as much searched for, but not equally, is going to be 80. Something that's going to be very little searched for, such as holiday, is going to end up having an index of 10. Okay. These come at the daily level, and they're quite useful also because they have a regional breakdown. What do these data contain? In a sense, if you want, they contain potentially useful signals of the macro variables that we're interested in. So, for example, the first economic applications of these are in labor markets. For example, you have Etterdredge, and then you have Atskis and Zimmerman. They look at searches related to unemployment, and they're able to use this data to forecast 3 months, 6 months ahead the actual unemployment numbers. This ends up being extremely useful, you can imagine, during COVID, when everything is changing at a rapid pace and we don't really know what's going on. And you will see one of the papers makes exactly use of that. There's the paper in 2010-2011 of Choi and Varian. Varian is the chief economist at Google, and Varian makes a point on how these various trends can be useful in time series analysis. And they go beyond labor markets. They are they're looking at applications for different things. The models were fairly standard. So you see here, this is an AR model, an AR2 model that was used. So you would just maybe use 1 or 2 lags for monthly or year-on-year changes. And again, this can be used in many other areas, such as forecasting house prices, forecasting price of transportation, and so on and so forth. During COVID time, these proved to be very useful because if you have a traditional macro data, which you see here on the left, that's hard and soft, so you have actual statistical time series and so on and so forth, you can use this very high frequency data to understand particular dynamics at much higher frequency. So in combination with these traditional variables, Google Trends have been shown to be quite useful. Again, they do not perform exactly the same across countries. So there's this chart on the right that gives us the four countries considered in the paper by Volodsko, which is an OECD paper. You see, during normal times, they track fairly well, but there's not so much variation altogether. For example, in the UK, they can miss a few peaks if you talk about Spain, and a few throughs if you talk about Italy. And generally, when there are very large swings in the economy, they don't necessarily pick up completely the contraction or the rebound. So you see, for example, the UK GDP is about -25. It's about -15 as indicated by the trends tracker, which is a combination of Google Trends. You can use them actually in conjunction with new models that help us understand which variable is driving the nowcast. And you have here an example from the same paper. So you see that some of them actually have economic intuition as we would expect them. So for example, more searches related to unemployment have a negative impact on GDP. Higher searches with investment have a positive impact on GDP, and they're among the highest. For the economies that were in the paper, so highly industrial economies, agriculture and forestry is considered to have a low impact altogether, and it switches between positive and negative. Of course, this then changes from country to country and from application to application. And on the right-hand side, you see how this can be used in order to explain the contraction according to different sectors of the economy. Again, here, the good thing is having that data available where you can actually go and see that a lot of the contraction was in consumption services, right? There's no restaurants, you can't go out and to a concert and so on and so forth. This has been extended, and for example, there's another model that in a sense it's quite close to the existing models that you have here for Switzerland, where a lot of very high frequency data from the financial market is used to construct a nowcasting index for Switzerland, again, to track GDP during COVID. The structure of the model is fairly simple. There's two factors, one external factor, one internal factor, and then these time series are then split between the two factors. You estimate them, and then you create this model that says GDP now loads on these two time series that represent the main important variation in the considered time series. What does the data actually look like for us? So these are the high frequency monthly changes, monthly indicators. So there's just two of them, otherwise it would have been impossible to see much. So there's Google inflation in blue and economy in orange across regions. And you can see already that you have, for example, Kyiv City has overall higher levels of searches related to the economy, as opposed to Sumy that has much lower levels of searches related to the economy. Of course, this does not tell us immediately something, but it does tell us that generally those people who look for things online, their interests are quite different, because again, on average, economy or issues related to the state of the economy are much more important to a Kyiv resident as opposed to a Sumy resident. And you know, the same goes for all the other variables. There are structural differences which are there, and you can kind of make up an idea why this could represent, in a sense, perhaps levels of education, perhaps employment structure, right? If you're an engineer, you're most likely going to look for, you know, particular issues related to your field, maybe chemical or physical processes, and so on and so forth. If you're in agriculture, maybe you're going to look for machinery or seeds. So those searches, even if they don't necessarily lead immediately to action across a large population, can be indicative of both future action as well as differences in the underlying population, differences in the underlying structure of the economy. What happens if we aggregate them? So these are four indices. Now they are no longer trends, they are changes computed quarterly for all of Ukraine. So you take all searches related, for example, to inflation, if you look on the right, and then you can plot the trend, but I plotted the change because this is going to be the input into our nowcasting model. And you see already what's that many of them have intuitive economic interpretation. So, you know, we have inflation targeting introduced by the National Bank sometimes in 2017. This was a big thing. Many people were looking at inflation. As inflation targeting is introduced, inflation becomes less of a topic in a sense. This is in a way a positive outcome. It says that there's not so much worry, if you wish, related to inflation following 2017. There's this persistent drop from 2018 onwards, and generally searches related to inflation are negative. So these are negative numbers, means every quarter we see some decreases in inflation searches. As COVID passes, we have this tremendous spike, which in 2020 could have been foreshadowing the type of inflation that we saw in 2021. And this again is a very interesting observation. What happens to travel? Again, you see that as COVID hits, very few people look for travel. There was some weakness already in 2019 as compared to 2018, but you see that this becomes negative for all of 2020, rebounds very strongly in 2021, but then again drops in 22. And export again tells us more or less a similar story. Now keep in mind that we have 35 such indices. And when we throw this into a factor model, we're going to have a 35 by 35 correlation matrix. So we're going to need some dimensionality reduction in this. Now, this is individual indices. How about the relationship between indices? Here I'm again switching to the regional data. And not only that, I'm also putting down something that we hope or think exists in the data, such as the Phillips curve, which is the relationship between Google unemployment and inflation. So this shows us the association for a particular region. In our case, we actually have one city, which is Kyiv. Searches related to unemployment and searches related to inflation. And the data is split on 2 different periods. Therefore, take it with a grain of salt. In any case, these lines don't actually represent so much. So before inflation targeting and after inflation targeting. And you see that for most regions, there was some positive or zero correlation between the two. We would have expected perhaps a negative. And then inflation targeting changes a bit the behavior at regional level between these searches. Now, again, this is just 2 of them. Keep in mind that we have many categories. So we actually have a lot of noise in the high frequency data. If we talk, for example, about the picture on the upper left, where we have the regional data, and we have many, many correlations to work with. So already there, we see that we need to reduce somehow our data inputs and try to extract as much as possible out of those 35 by 35 correlation matrices. Now, the models that I was referring to before are meant to do that. So dynamic factor models, as Giannone, as Dodds, as Bambura, and so on and so forth, they create a state space model that relates some latent factors, unobserved factors, usually between 4 and 8, that drive 20, 30, 50, 100 observed variables. This is, in a sense, the prototypical structure that tells us there's a state space equation. The second equation, FT, is a sum of AI, FTI. This can be a matrix. There are connection between our variables across time, and then our observed factors, XT, load through lambda on the unobserved factors. And keep in mind that our XT is going to be about 100 variables being explained by just 10, for example, latent factors. So you see that huge amount of data gets compressed in a much smaller representation, which can be very, very useful once you work in a macro setting. This can be estimated either using maximum likelihood, or you can employ simple common factors estimation by principal components, and then these factors, which are going to be the principal components, are then used in a second stage to run this first equation and retrieve these lambdas. So how each individual variable loads on them. Now, this estimation technique comes from multivariate statistics and tries to take that large matrix of variables X and produce a lower dimensional representation in terms of principal components. So you see, I'll switch between principal components and factors. They're quite usually they're used both at the same time. The kind of problem that gets solved, it's actually a problem of finding loadings of the existing variables on these factors. And in machine learning, this is an unsupervised problem, optimization problem. We're just interested in reducing a large number of variables into a smaller representation. So we want to represent the variance in X through the variance in a smaller number of factors. And this is a little bit what the optimization problem would look like. Singular value decomposition is what's normally used. You look for the first 3, 4, 5 eigen values of X and the corresponding eigenvectors. When you sum them up, they're going to be able to pick up 60–70% of the variance in X. But instead of having 100 time series, we now have just 10 time series. And you're happy with the ability of using just those 10, even though you know maybe about 30%, 35% of the variance in X is not actually captured in your model. What's the inherent assumption here? That's very important. We assume that variance is equal information. Information about what happens in the second stage when we regress Y on our factors. That means when we regress GDP on the factors. And we will see that's not always the case. And that's even less the case when we talk about Google Trends, which are not actually economic data, but we hope are proxies of economic data. So this is normally what PCR does. This is a very simple example. It shows us for two variables, keep in mind we're going to have 100, what PCR will give us. PCR will give us a rotated view of our data such that the extracted latent factors are going to be independent of each other. So if you just look at the cloud of green points, we have a highly positive correlation between x1 and x2. And if we were to put them in a regression, y on x1 and x2, we kind of know what would happen. If we are worried about that high correlation between x1 and x2, we could produce the PCRs, which are the purple lines. And the purple lines are still going to be two vectors, just that now the correlation between PC1 and PC2 is going to be 0. They're perpendicular on each other. Once we have these independent factors, we can throw them into a regression equation and hope that they contain relevant information also about y. But you see from the onset that the type of algorithm is very much about explaining variance in x, whereas what we're after is understanding y. We're actually after understanding GDP, not necessarily compressing a very large number of variables into a smaller number of variables. So is there an algorithm that perhaps can deal with this? Yes, the answer is there is one. It's called partial least squares. It's a very close cousin of PCR. And this is used extensively in bioinformatics, in medicine in general, in modeling how the brain functions, any area in which you end up with a small observational sample and a very large number of potential explanatory variables. Now, the algorithm, there's more details in the paper that's online. The algorithm will produce latent factors, but will produce latent factors that fits two objectives. One is to capture the variance in X, which you see here, but also to capture the correlation between X and Y. So in a sense, what this algorithm does, it goes through a series of calculations, such as to produce latent factors, independent one of the other, that not only explain the variance in X, but explain the variance in X and their correlation with Y. This is particularly important for us, as if you look at the Monte Carlo studies of how these algorithms work, you take the same large data set. So you might end up with whatever your 1,000 explanatory variables and only 100 observations. And you will see that normally for the same data set, you would need about 7 principal components to achieve the same performance in terms of prediction as 2 PLS latent factors. So that already tells us, in an application where we might have very little data, which is exactly what we're after, PLS is going to be preferred because we're going to have far fewer variables needed to achieve the same prediction ability as many PCR would. Okay, so from the onset, this looks like a good choice. What is the representation and what is the structure of this? This is a simple graph showing us the relationship between variables. There's 2 latent factors, L1 and L2, that drive X1, X2, and X3. Keep in mind, in reality, we do not observe L1 and L2. What we observe is X1, X2, X3, and we try to guess, if you wish, what the L1 and L2 are in order to be able to compute Y. In macro applications, as is this case here, we would also have some arrows pointing from X1 to Y, X2 to Y, and X3 to Y. Each arrow represents an influence of that variable on the variable on which it points. Okay, so this would be a simple example. There's code in the paper that you find online that allows you to play with this example and shows you that in a particular case with about 10 variables, and if I remember correctly, maybe 50 data points or 40 data points or 100 data points, I don't remember exactly, you will see that PCR actually is not able to recover as good as PLS these latent factors. And again, the algorithm is explained a little bit in the paper, and this reference, Vold 84, is very useful. There's a bunch of other references that explain a little bit how this is, as well as the book by Friedman. So the modeling, now, we talked a little bit about the data. The data is not what we wished for. This new data requires a new model, but how can we work with a new model? Again, we go back to understanding the behavior and performance of this model, given the kind of applications that we have. So we have possibly a rich cross-section of explanatory variables, but it's too rich for 34 quarters of national GDP, if we talk about 2013 to about 2021. And keep in mind that if we talk about yearly data, we settle for just 9 years of data, as very, very early data actually represent a fundamentally different economy. So we need to somehow shrink these data. That means compress it into fewer factors. The shrinkage is useful. So shrinkage means to make something small, and it refers to making parameters small in a regression. This adds benefits in interpretability of a machine learning model. But can be unstable if we think that each oblast might actually have its own economic profile. So we can't actually just pull together all the data and assume everything is the same. We can use PCR, but there again, we lose interpretability, and keep in mind that we would need many more PCRs to get the same forecasting ability as PLS. Therefore, we end up with PLS, and inside of PLS, we also find out that for contexts of small number of observations and large P, very large number of potentially explanatory variables, there are particular techniques developed to select what is useful and throw out what is not. For example, genetic study usually have 30 times more variables than they have observations. So again, we're almost there in terms of this ratio. I think in this application is about 25. How do we get to sparse outcomes? So how do we regularize? How do we throw out information that's not useful? This is a tremendously large literature, and there's many ways to do it. In PLS, there's several applications, and they usually belong to different families. So they're either filters, wrappers, or embedded, depending on the type of work that they do with the data. So Chun and Kelesh is an early application which takes that optimization problem and introduces, just like in Lasso, introduces a sparsity step. So it puts a penalty on particular variables that have very high variance but don't explain a lot in Y. So X might have a lot of variance, but it doesn't explain a lot of Y. It gets a very small parameter, even 0. And by doing that, it basically excludes variables that might not be very useful. So the typical PLS works like a rich regression because it puts a weight on each individual variable. But if your variable is actually noise, you might be fitting noise. And this is where the sparsity comes in and basically throws out the variable that might not be useful. There's different techniques. So this one is an embedded way. There's also forward or backward variable selection. There are lasso-like solutions, and there are solutions using genetic algorithms. So for our applications, there's 2 different solutions used. The first one is the wrapper, the genetic algorithm selection, as well as the embedded method of Chun-Kelesh, which is called SPLS. So you're going to see 2 variants on the charts. Is going to be the genetic algorithm, and is going to be the SPLS. This is a very, very brief overview. I just wanted to show you on the right-hand side the variables and the lags which are picked by the genetic algorithm. The genetic algorithm, in a way, mimics how genes evolve. And if you want, in 20 seconds, it creates different subsets of variables which are either included or excluded depending on their ability in explaining why. the explaining of why is done through a model. So GA can be a variable selection in an OLS model, it can be in a PCR model, and it can be in a PLS model. In our case, given the structure of the model, GA is actually used on PLS. So imagine that you're running thousands of subsets of different variables that try to target Y using the PLS algorithm. This is your first population. Those subsets that contain the most useful variables are included in the next generation, and they can be mixed, so there's crossover, or they can be mutated. That means sometimes they're in, sometimes they're out, but generally they survive in the population. That means they have higher fit in their ability of capturing Y. What explains GDP in sample? If we look at quarterly data, you see here, so L1 stands for the first lag, no underscore, anything means that the concurrent value, so the current value. You see that searches, for example, searches for inflation generally have negative impact on GDP. So past searches in inflation have negative impact in GDP. Interest rate searches have positive, both current and lagged impact on GDP. And emigration has slightly negative values on in terms of nowcasting and so on and so forth. Right. So I was just talking about all these models, and I was saying, okay, they have different forecasting ability and in sample ability. So let's just look at the models. So here you have the families of model. DFM stands for the dynamic factor model. This is what we normally use when we have a lot of good economic data. GAPLS stands for the genetic algorithm selected PLS. GDP is the actual data. The red is the observed variable. The gray is the standard PLS, and SPLS is the Chun-Kelesh embedded method. There's a lot of agreement in terms of the PLS methods. There might be a bit of variation here and there, but you see that the dynamic factor model has periods in which it underperforms or overperforms quite substantially. The same goes for 2020. For example, GAPLS is able to fit very well in sample and is able to pick up also the recovery quite well. SPLS overestimates, dynamic factor model underestimates. Again, this is not surprising. Keep in mind that dynamic factor model is a two-stage which does not target GDP. PLS targets GDP through the variation in X, right? So the way you compute the factors is fundamentally different there. This is a zoom just to make sense of that. The chart is the same in sample, but just shows you a smaller time frame just to make sense of that data. How does this work if we now switch to our regional application? Well, actually, this works quite well, even though, keep in mind, we now have 9 data points that we're working with. Okay. All of the models that you have here are models that have 2 or 3 latent factors. So again, it doesn't sound like much, but you know, a regression of 9 data points on 2 explanatory variables is producing this. By the way, how do we know that this kind of makes sense, that this is not complete nonsense? Well, one way is to use GDP weights and see how the regional factor model explains aggregates by simply looking at their sum according to the weights that they have in GDP. So keep in mind that we had before red was GDP, now GDP is green, and the old PLS versions are dotted, PCR versions are solid. And you see that PLS tends to match much better in sample than PCR. What happens with the actual, with their actual performance, forecasting performance? This is the exercise where we use the parameters as estimated, as fitted for the period 2013 to 2021. And we use the observed quarterly Google Trends as they were happening in March and in May, June. And what you see here in red is the actual GDP, and then you see the variance in SPLS, GAPLS, and traditional PLS. And you see, for example, in this case that, yes, the direction is picked well by all three, but they give us different pictures in terms of the magnitude of the contraction. There's another exercise. I don't have time now exactly to talk about it, but you can look for different combinations of variables and number of latent factors that produce even better fits for this out of sample forecast. So this is what the model would have told us the GDP was contracting at in using just the GDP, just the Google Trends data. The bottom is that model, but now using regional highly relevant cache data. So I was mentioning very briefly in the beginning that cache data can be very useful. We take the same regional model, but instead of using Google Trends, we use something that we know works very well, such as cache turnover, which is something that we have at the regional level monthly. And we use the yearly parameters to very standard bridge equation to now cast total aggregate Ukrainian GDP using the 25, basically 25 models. And you see here that in November, so the gap, the drop in this is now year on year, this is subsequent periods contraction, the top is quarter on quarter. So you see that the depth of the contraction is very well picked up because this is almost 40%. And then you see that the final year minus 29.1, which we knew in March, April this year, was already being sort of pointed out by the model in November. So in November, there's this minus maybe, 28, 27. So again, keep in mind that the bottom that works very well has both the model that targets GDP, but also highly relevant data. So some final considerations. There's still lots of work to be done and to check. And in the paper, I'm trying to provide a couple of extra details. There's also different ways to select the variables, to interpret the variables, and so on and so forth. So there may be non-trivial benefits in estimating latent factors using partial risk squares as opposed to PCR. Sparsity can be quite useful because it improves estimation performance and it allows us to get better interpretability of the model. We now no longer have 10 factors which load on 100 variables, but we might actually end up just with 2-3 factors loading on 20 variables. And this makes the problem much more manageable. And the other thing that's worth investigating further is this ability of geographically disaggregated data to give us a good nowcasting and forecasting, potentially forecasting performance in GDP. And that's about it on my side. If you have any questions or comments, please let me know.
Thank you, Mihnea, very much. Do we have questions? So I will take a chance to ask a question. So you know that Google usually, they had a couple of events or a couple of periods when they changed methodology for some countries or some specific regions. And basically they even have a note there that since this time there is a change in methodology, basically which makes it problematic to compare different periods. Yeah. And here in 2022, after the start of the full-scale invasion, in about 2 or 3 months after February 24th, they also changed the methodology, and there is also a note there that it's changed. Do you take it into consideration somehow, or?
Yeah, unfortunately not, because it's not clear what that change is. Keep in mind that what we actually know quite little about how these Google Trends are made up. So we know that Google has an algorithm that picks certain keywords and puts them inside of a category or in a trend. But we do not know exactly what they pick, because if you think through the lens of our model, they are already doing a form of variable selection by selecting certain search words to be represented in a particular trend. Now, methodology could be that they change the weights that they put to different keywords, they exclude certain keywords, or they put certain keywords in. I tried to look at how stable these things are. For some categories, there's not so much change. So my guess is when they talk about methodology, they generally reflect different population changes or things like this. So, of course, this is not very satisfactory because we don't really know how they change our input data. But again, you know, we can try to test this over different periods to see if things are fundamentally different. At the end of the day, there can be changes. I'm sure they would be reflected also in the performance, but not to the level of the contraction that we saw, right? So in normal periods, probably this would give us that extra 0.5% above or below that should make sense when we talk about 2% GDP. But when we talk about contractions of 40%, you know, if you miss by 5%, it's perhaps not so much of a worry, as opposed to not having any estimate. So I think at the end of the day, it's also important to put this in the perspective of what do we do when we don't have other data, in a way.
Yeah, it would be interesting actually to compare the results by taking this initial data that they provided in first month. I know that we have this data because, for example, the project that you worked with Nicodem and Kalle, the first version actually includes the data without any change.
Yes.
And only afterwards they kind of retrospectively changed the data. So probably it would be a good idea to change it so we have kind of a real life real life exercise when the data comes as it is. This would be interesting. Okay, and also, yes. Another question is when these factors are computed, do they actually depend on the period that you take? So, for example, whether if you stop your exercise this month, your factors will stay the same as you extend 1 month later.
Yes.
Or so, you recompute everything and factors are different for the entire history.
So for the policy applications that we discussed with policy colleagues also, every time I get a new data point in GDP, I update the model. What you see here is fixed in time in the sense of trying as much as possible to replicate the exercise in March, April, May, when we had data stopping in December 2021, and we had data on Google Trends for that particular month. And the only thing we could try to do is to infer what GDP could be based on whatever we had available. But of course, once GDP was published, you can update this, and then you see this immediately in the estimates. So, you know, even, you know, you were mentioning before different vintages of data. The November nowcast of about -27 for 2022, this was revised quite fast as soon as we had, and it produced a different nowcast for Q1 2023, as soon as we knew that the drop in 2022 at the end was not 31 or 32 as it was initially, but it was 29. So it feels it's small, that 3%, but actually it changed the nowcast, it improved the nowcast for Q1 by about 2 percentage points. So it shows that the model is fairly sensitive to these kind of things. And I guess that as soon as we have enough time to look at more details, you know, these we can work with different vintages of data with different specifications to see how this goes.
Mm-hmm. One way actually to take this, like to get some profit from this, is to evaluate the performance of each model given the different vintages, and then for each next nowcast kind of provide a weighted average forecast out of these models, which may actually help to identify which model was better in the past. Yeah.
Absolutely, yeah. I mean, the cheapest way to solve this problem is just take an average of the 4 estimates that you now have. And you see that we get very, very close to what happens in reality, because some models generally overestimate, some models generally underestimate, and some just play in between. So even without sophisticated Bayesian methods of weighting, averaging out these nowcasts can actually be quite useful. That's very true.
Actually, if I may, the last question from me. So we
Sure.
have the preliminary estimates of the State Statistics Service. So the current our knowledge about GDP is still the estimates of the State Statistics Service. You're right. So is it possible in these models to use this to improve the nowcasting performance? I mean, like if the model fits better, if the nowcast fits better to the official estimates, then kind of we grade this model better or something.
You mean in their ability? Yeah, I mean, what we could try to do, rather than talk about nowcast, is actually try to use the same data in different setup to build a forecast, and then see at which, Q1, Q2, Q3, at which forecasting horizon it works better. And then see if it works better for certain vintages. So if it works better, for the first prints of Q1, maybe it works better for the second prints of Q2, stuff like that. So this can definitely, in a sense, be done. Because I'm thinking that at the end of the day, even if it's an approximate, this is still useful information, right? So it's very useful for the model to know that you might not actually have minus whatever 20, it's just minus, between brackets, just minus 11, for example. So this is very useful information.
Mm-hmm.
Yeah.
Because we don't know how they do these estimates. It's a big mystery.
Yeah.
Anyway, are there any other questions? Okay, so just let me make a final announcement. So just recently, a couple of hours ago, we published online a working paper of Mihnea on this topic. So it is now available on our website, and you can easily find it and probably read. So Mihnea will give the presentation on nowcasting during the conference. So please join online. There will be a possibility to watch the conference online. Tomorrow we are going to have another open research seminar by Tofam and Alexander Talavera. They will be talking about labor markets in Ukraine and Poland after the start of the full-scale invasion. So they are using online online vacancy data to evaluate how the war affected the labor markets in Poland and Ukraine. So everyone is welcome, and I hope to see you tomorrow. Thank you, Mihnea, very much one more time for the seminar. It was very insightful and interesting. And I just want to mention one more time that it helped a lot the NBU in this nowcasting process when we were not able to get the official data and other sources of data, and we were kind of struggling to understand what's going on in the economy. And this was one of the projects which helped us a lot. So thank you very much. Have a nice day and see you tomorrow.
Great,
also,
thanks all.
We have one question from Marina.
Yeah, sure.
Thank you so much for an informative investigation that you conducted. And I've got an organizational question. How can we get the recording of this wonderful seminar today?
So the recording will be also published. The link to this record will be published on our website in I don't know, in a couple of days or something.
Thank you so much.
It will be available, and slides as well.
Thank you so much.
Okay.
Good day.
Good. Then thank you very much one more time. Have a nice day. Goodbye.
Thanks. Bye-bye. See you all.
Thank you. Bye.